Okay, let's blink an LED. We're going to turn it on, then turn it off again, but slow it down so that we have some half chance of seeing it blink. This will include watching it on an oscilloscope using an analog discovery too. First up, new project. What is this? Blink? 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 Low. Blink. New location. Doing this on my H drive. Where did that happen? Slow. Blink. Folder. Select. Okay. Okay, we're going to just roll with this template code here. ATtiny85, great. We're going to scroll all the way down, and we're going to use this .def for RMP, multi-purpose register .def. Now, instead of saying register 16, I will use RP. Right? That's the only register that we're going to actually. We're also not using any variables in RAM. So we can just skip on through there. Here's our code segment, starts at address 0. Here's our reset vectors. Remember, all of our other code so far has jumped, has continued, and just ran our code right in here, 3 or 4 instructions. This is what happens if we have resets enabled or interrupts enabled. Main interrupt is the reset vector, all these others. We're not using them, so this instruction will just jump to our main label. No problem. Here's our main label. That's it. We are going to definitely not enable interrupts. I do not want that. What is the stack pointer stuff? I have absolutely no idea. Yeah, and let's change this around a little bit. I'm changing my. I'm going to make a label here, init. I want to set BI DDRB. I'm still using pin 3. 3. Pin as an output. That's it. Careful, my jump to main. Now actually I jump to it. Otherwise we will have problems. Here's our main. Main program loop setup. I don't delete, 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 and I'm looking down here at the bottom. Stick this here so I can better. What are we gonna do? We're gonna set the pin high. Set pin B3 high. That would be SBI port B pin 3. No problem. Later we'll have a CBI, a clear bit, port B pin 3. So this sets pin 0. I don't really care for this text editor. What are we going to do after that? We are going to R jump back to main. Just try it out. Save it. Okay. Assemble this. Okay, we assembled without errors. Assemble without errors. For me. I want to upload this. Remember, I go to my command shell. Look where I am. CD into slow blink. into here. I have a hex code here. Paste in this, and you notice that this is not blink.hex. This needs to be slow. Enter, and it programs. So I'll do that one more time with the document camera up, so you're not looking at me. Up arrow, enter, programmed, LED turns on. All right. If you notice here, I have an LED. These two pins are my analog discovery 2 input channels, number 1 and number 2. The minuses go to 0 down here, and then the pluses, those two input channels, goes to physical pin 2 and physical pin 3. You can area. I'm just looking at physical pin 2, which is PB2. We'll see what's up with the other pin here in a minute. All right, here's waveforms. Waveforms. I want to turn on the oscilloscope. Big. Run the scope. I like to set up my scope with offset as divisions. Helps. It makes zooming just be a little more intuitive. It's like the hardware oscilloscopes. This looks like a big hot mess. I'm going to turn off channel 2. Actually, it's just channel 2 that's hooked up. So channel 2, this looks like a mess. Remember, I'm toggling this really fast. I need to zoom in. Doesn't look so good. Well, actually it looks better than you might expect. My trigger, my signal's actually on channel 2. I'm going to trigger on channel 2, put this way up here. Turn the physical stuff off here for a second. Okay, scroll down so I can see this. Scroll that way. All right, you can totally see that this is not 50% duty cycle. Look on the right side, move my trigger off of here, and it's going all over the place. That's the whole idea of trigger. So here's trigger, here is 0 seconds, and this is where we cross that slope, our trigger event. You can see these glitches. If I zoom in just a little bit more, I'm going to do 1 microsecond per division, shift my 0 over to the left side here. 1 microsecond, 2 microsecond, 3, so on. If you remember from the data sheet, which if you don't, we're just going to go all the way down to our instruction set summary. SBI. Go. So we have SBI. We've been using that. And PDF viewer. See, this takes 2 clock cycles. Now, the AVR that I have here that I programmed, I literally took out of the tube. It was bare. And the default for that is 8 megahertz clock with divide by 8 clock divider. So our clock is actually 1 megahertz. And that's how the simulator is set up too. It says 1 megahertz here. But the other thing is I can tell it's about that is because I stay high for 2 clock cycles, and then I go low for 2 clock cycles, and then I have 2 more clock cycles. Remember, we are jumping back to main. In our jump, go back to the data sheet, roll up here. In our jump takes 2 clock cycles. Isn't that great? So of course, this is exactly what's happening. I want to see what's happening with the clock. If I turn on channel 1, I just see this. This is at 0. We make sure these are the same volts per division. And this is actually just kind of interference stuff. I don't have anything output on this. What I really want to do is I want to go back to my data sheet, take a look at this, bookmarks, go to, oh, I'm almost forgetting, system clock and clock options. Actually, let me come up to the top and search CLK 0. Actually, it's 0. Clock output, clock input. So PB4. We'll click down here, searching clock output buffer. Device can be output the system clock on this pin. So we can actually see what clock we have, just set it to a pin. We don't have many pins on the AVR, but PB4 is available. So how do we do that? It says the CK out fuse has to be programmed. And what am I going to do? Going to right click and search. Look up. Go CK out. I want to know what fuse this is. Dictionary. So CK out. Search for that. And we're going to hit on the fuses. All right, fuse out. Find the fuse. Please find the fuse. Here we go. Here's the fuses. I'm going to scroll up to our extended byte. Extended byte. We definitely want self-programming enabled, so we're not going to change the extended byte. The high byte, external reset disabled. We want that, This is default, 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 default. And we're going to keep all of this. So we go down to the fuse low byte. By default, our clock is in fact divided by 8. CK out is a 1. This is enable it. I put this to a 0. I enable the clock output. That's what I want. I don't want it to touch anything else in here. Well, let's check out how we do this with AVR Dude. So here's AVR Dude. I am indeed hooked up to COM3, and I want to write I want this to be L fuse. I want to write this, and I want it to be binary value and in do this all at the same time. Alt tab between it. 0 is 0, that's my change. 1 0 0 0 1 0. Okay. 0 0 1 0. And then 0 0 1 1. So changing clock source 0 0 1 1, internal 8 megahertz RCI. Please don't mess this up. 0 0 1 0 0 0 1 0, and immediate. That means this is not a file name. This is the bits that I want, or the 8 bits in fuse. If I hit enter right now, you will see program. The lights blink. Lights blink. 1 fuse, L fuse verified, and we have this clock here. Switch over to waveforms, and now we have channel 1 is hooked up to PB4, and it's showing the clock. I'm going to move this up so we can look at this a little better, and we see in fact that we have 1 edge, 2 edge. This duration is for 2 full clock cycles. That's how long it takes. Actually, it's probably, I'm not exactly sure. I think here. This, after the instruction executes, it's not like we read the instruction and it turns high before we're done reading the instruction. I think that the instruction is running, I'll go right here in this, and at the very end of that instruction, when we go to read the next instruction, this rising edge makes the data show up at the output register. So it's from 4 to 6 microseconds that our set bit high is actually being loaded and decoded. And then when we're finished after the second clock cycle, bam, it goes low. But it sure looks like it stays high. and then it stays high for that we do something else. And you can totally see that's the relationship between the clock and the output. The clock is going a lot faster than. Is the problem? I don't know. Let's check it out. Machine is not liking that too much. All right, here's our R jump. I need to delay now. How do we delay? Well, I need to count up or count down. What we're going to do is we're going to read a number into a register, decrement it, because if we go to the data sheet, see that we get an instruction. Go down to our instruction set summary. That we get DEC, decrement. We can also get an increment instruction. We tell it the register. You'll see why decrementing, start from an upper count and going down, makes a little more sense. Or it's a little easier in a sense. So we're going to load an immediate into our multi-purpose. I'm going to just call this register by its full name, register 16. Register 16, the immediate value is do a 4 for now, so we can watch this happen. Let's do FF. Load FF into this. We're going to decrement register 16. What do we do when the register is hits 0? Well, remember, I want to go from here back up to decrement. I don't need to load it again. And I want to decrement, 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 all for 255 instructions. Okay. We can get one more out of this by messing with the unsigned overflow. I'm not going to do that right now. Minimize the confusion. Here we go. What do we want to do? R jump. And we need a label. Do that. Call this loop. I'm using uppercase letters for my labels. Well, we have a problem with this is we're always going to do this. We need to make a decision. Make a decision that is called branching. Go back to our instruction set that we have. Branch instructions. R jump always works. I jump always goes. R call, these are function calls, returns. We want these branch. Branch if the status flag is set, branch cleared, branch if equal, branch if not equal. Okay, so program counter goes to the next one, or it doesn't go to the next one, it goes wherever we ask to jump to if it is equal. Okay, equal, what is the equal? This is actually the, you can look in the instruction set manual, I won't. Now let's do that. Branch if equal, we'll go all the way down to BREQ, instruction set manual. If 0 flag is a 1, then we jump. Otherwise, keep going. What we want to do is jump backwards if it is not 0. When we decrement, if it hits 0, the Z flag goes to a 1. I want Z to be 0. You'll have to think about that for a second, but I want to loop if we're not at 0. Okay, so BREQ is not what I want. I want BRE. BR branch if. That's the instruction. BRNE, back to loop. If our 0 is, if this is false, fall through, we set it below. Okay, great. Save this. We're going to assemble this, assembled without errors. We're going to program X. Previous command was my fuse. Do that. Watch what happens. Programs, programmed. Here we go. On. Go back to waveforms, run this. Ooh, longer. Zoom out. It goes down for how many clock cycles? 1, 2, 3, 4. We've seen 4 clock cycles. This off. Keep zooming out. Oh, zoom out. So that's good. I want to stay. Now I want to go low and stay low for a long time. I need the same thing happening here. All right, let's do it. Set it low. We LDI register 16 with my constant. Here's my constant. I want to loop. Okay, and decrement register 16. BR not equal. Back to loop. That's our second delay. We go to main. Done. Assemble. Failed. Fail. Fail. Line loop. Line is 111. 11. Loop symbol or register is already defined. What's up? 11 error. What's up? Oh, see the problem? See, we have symbols defined twice. The assembler thankfully helps us out. Let me call this loop 0. You change it in both places. I'm going to call this loop 1. Now, loop 1, loop 0, round assemble. Errors. Here. Up. Flash it. Great. See what we have. Let's run the scope. Hey, this is good. Oh, high. Oh, high. Let's look at some measurements. Click on the measurements. Okay. All right, measurements. Find on channel 2. Onto frequency, period. Duty, positive. Which of these? Twice. Move. Here we go. 600 hertz. This is still way too fast to see. But now we can see that we have slowed this down. Be careful. See how the duty cycle? You can get exactly 50% duty cycle. I'm going to have to leave that to you to figure out. That's what lifetime is. All right, how do we slow this down even more? Well, the problem, really a problem, is our registers only hold 8 bits. We can count down 8 bits. So maybe we have to count down and count down. Check it out. LDI register 7. Yeah, do this. Register 17. Okay, I'm going to call this loop 0, 0. Okay, this is really horrible naming. So we go here, and then once we get to here, increment register 17. Not done yet. Go back to loop 0, 0. Just assemble and program this. See what we get. Assemble without errors. Program. See what happens. Turn that on. Programmed. And this is still kind of fast. See what happens. Run. Okay, this is a lot slower. Very good news. On. Do the same same fancy pants trick. Loop loop, and 1, D, do that. Abort. LDI, register 17, FF. What are we going to do again? Okay. Okay. But that helps for spacing is horrendous. Okay, so LDI. Next one, decrement 16. I'm getting all confused. Do what? Paste. Oh, here's a loop. Inner loop. Outer loop. Here we go. Okay. Symbol. Symbol without errors. Turn that on. Program. We're going to see a program. And we're going to see the scope update right away. Look how slow that is. And now our light is blinking much slower. It is still not exactly 50% duty cycle. We're off by a few, but that is how we do a blink. That's how we do a loop. Doing loops in assembly aren't too bad, but you do have to do it in a different way. This is like a for loop. We did a double for loop today. Thanks for watching.